Thank you.
Thank you, Morris. Again, good afternoon, one and all. I promise you this session, I won't put you to sleep for sure. Okay, so this, as Morris mentioned, this is the second masterclass. The first masterclass was, we talked about elements of hybrid, where does edge come into play, what are some of the infrastructure investments, and if you guys missed it, no problem. We'll touch a few of those concepts in this session, and then I'll hand it over to my partner in crime from Layla Networks, and he's going to walk you through real examples of running large models on device, and George is standing there. And after that, we'll have about 5 to 10 minutes for any open questions. You want to beat us up, no problem. Okay, starting off, the AI inference, right? I want to kind of present the picture on where is the inference actually heading, moving forward. Historically, as everyone is quite familiar with the fact, inference in the cloud is what is happening. It is easy for sure. It provides the scale and the reach. But at the same time, inference is also being happening on the edge for quite some time. Qualcomm has been positioning inference on the edge because they're able to support better user privacy, better responsiveness, faster latency, and most importantly, personalization. These days, they always joke with my kids is inference today lacks common sense. And if you really want to make sure you want to transition from a generic to a personalized inference, you need to have a lot of contextual information. You need to understand the emotional intelligence and the preferences and the choice of the user. You're able to augment that to these large models by collecting data on the edge. Now, I'm at the same time not saying that cloud is not necessary. It's absolutely important, but you do that only for scale. If you want to look at large reasoning models or large models that cannot be hosted on the device, at that point of time you go towards the cloud. And at the same time, you also have concepts of hybrid, and hybrid is also exists today. In the way the hybrid is set up today is very much predefined. If you happen to have a certain task, if somebody comes and asks, tell me what is the weather pattern in the planet of Jupiter, right? Some crazy question like that. Then by definition, the edge doesn't really have the intelligence to answer those questions. It obviously goes to a large model on the cloud and gives you the best response available of the reasoning models. But what we're looking for from a Qualcomm perspective is to work with partners and look at dynamic routers to support hybrid inference. What that actually means is the inference always starts on the edge, and at the edge, at some point of time during a conversation, let be a multi-turn conversation, is not able to help the user. At that point of time, dynamically shifts towards the cloud and takes the contextual information in the background or the connection of the conversation with the user, so it's seamless as you transition from the edge to the cloud. And I'll be the first one to admit that flavor of dynamic hybrid is difficult. It's not easy, but at Qualcomm we love challenges. So this is something that we're kind of working on, and we're trying to move from static hybrid to dynamic hybrid. Okay, so that being said, let's move on to why edge, right? As I kind of already talked about, it's privacy, personalization, latency, responsiveness, all is good. But you can always ask the question is the models that's being developed by the ecosystem, is it really good? Is it ready to handle some of the most complex tasks? And I strongly believe it does. The quality of the small language models has improved quite drastically. People call it SLMs. And this is able to support a lot of domain and task-specific functions, either in the productivity domain, content creation domain, content consumption domain, and multi-such domains. And at the same time, it's just not the strength, the number of parameters of the model, but also we have a lot of context length that kind of gets baked in to reduce hallucination. Unimodals are becoming multimodals, wherein you're able to put in image, text, video, time series data as part of the prompt, mix that, and then provide a certain prediction and outcome for the user. So the ecosystem is putting a lot of effort into this because they truly believe that SLMs are the future to really drive what you call synthetic data creation, either for generative space or for agentic space. So given there's been a lot of push and the quality of these models are working through, we have a lot of strong partnership with model creators to use that asset and build a lot of interesting applications and use cases around it. And at the bottom are some of the model makers we closely work with. We do, also geo-specific models. For example, elements like Tech Mahindra is something, that they want to emphasize for Indian ecosystem language models. Tech Mahindra really helps. Same thing with Mistral. We work with them with a lot of, SLM models, which are extremely good in the language of French, and kind of deploy that in the region of France. At Qualcomm, for us, scale is very important. Whenever we develop a solution, it's just not just for one swim lane, for one form factor. Qualcomm has a very strong footprint from phones to AR glasses, smart glasses, virtual reality, IoT home devices, to PC computers, to automotive IVI, automotive ADAS elements. And when you're trying to have scale and you want to deploy it across multiple edge-based form factors while operating in multiple OS, in Linux, in Ubuntu, in Windows, and Android, it's not an easy problem. You already have complex set of variables that you have to work with. The most important element to really drive scale is you need to have a consistent stack. Stack is just not software. You need to make sure you have the right tools, you have the hardware architecture, right system configurations to be able to develop once from an application standpoint and deploy it across these swim lanes quite easily. And that at Qualcomm we're able to do it. We've been doing it for the last 10 years or so because of a consistent stack that we maintain across all these swim lanes. So how do we do that? So I'll kind of walk you through some of the journeys that we have. Now today, when you look at these large models and many of the traditional developer-friendly frameworks, the Olama, the Hyperlink, coming from the Nexa team, anything LLM, LM Studio, are very much cloud-centric. When I mean by cloud-centric is they work with these cloud provider, the model providers, either coming from Meta, Microsoft, or IBM, and they create, I would say, a Docker image or a web UI interface, thereby able to deploy these models a lot more easier. Yes, they are working on implementing on the edge, but to a large extent it started off on the cloud, and the cloud interaction is a lot more popular. And I don't blame anyone because it's, as I mentioned, it's easy to deploy. It has a scale, it has a reach. You're able to do that quite seamlessly across multiple geos. You don't really have much of a problem. But we're trying to really work with the ecosystem and show why it can be done on the edge. But before we do it on the edge, it's also important to understand, does the edge have the necessary infrastructure? Does it have the necessary compute elements to really make the user experience a lot more seamless? It does not impact the latency or the interaction. So in this case, I'll kind of highlight specifically on two domains. One is we have the general purpose compute machines like the CPU and GPU already available. You could always use that to deploy a lot of these models on the edge. Then you have the Hexagon NPU. The Hexagon NPU is a domain-specific AI engine. Here we have significant amount of compute, or what we call as flops or tops or GMAX, whatever nomenclature you're familiar with, that's invested in the Hexagon NPU. Why is it important? Because that compute block is able to provide you better latency, faster time to first token, or any kind of function that needs matrix acceleration. You're able to get that done as part of the Hexagon NPU. The Hexagon NPU, we have three fundamental blocks. We have the tensor unit, the scalar unit, and the vector unit. The tensor unit is all about the matrix blocks, which I just explained. The vector engine is really is expected to support all kind of vector operations. So when I talked about earlier, large models are now also coming up with large context length, 4K to 8K to 16K to 128K, to be able to drive personalization. Whenever you happen to have large context length, the KV cache becomes a bottleneck. So to accelerate KV cache, we put a lot more investment in vector cores to really make sure that it does not hold up speed up of operations and does not impact your end-to-end latency. The scalar unit is slightly different. Here, again, in the elements of deep learning network, everybody is familiar with dynamic shapes. When you're looking at image creation, video creation, you can have an image input size of 256 by 256, or you can have a dynamic input shape with one frame being 256 by 256, other frame being 1K by 1K kind of elements. So to really support these variable lengths, either be image or tensor or any other word format, we have investments in Scalar to really support and supplement that. Again, three fundamental blocks to really make sure the inference on the edge is not compromised using Hexagon NPU. We also have a few of the new data types. Everybody is quite familiar with the floating point representation. This year on Snapdragon 8 Gen 5 platform, we introduced the FP8. So if people are using the latest cloud infrastructure to develop FP8 models, you're able to infer that on the edge with any kind of transformation completely natively on silicon as well. And if you're very constrained on memory, we're able to compress these models into 2-bit representation, and then we have native int2 support so that you're able to support large models. In the last session, we showed you that we now have 14 billion reasoning models running on the edge using int2 support. And obviously, in this masterclass, I won't go into these intrinsics, but if there's any question, outside this class, I can kind of walk you through some of the specifics. This chart kind of showcases where do you use the different data types. We have the y-axis is the power, x-axis is the compute, and most of the edge-based devices is a lot more investment on fixed point representation. Fixed point representation meaning int 8, int 4, int 16 kind of stuff. A floating point representation is float 16, float 8, float 4 kind of stuff. If your use cases is looking for sustainability, meaning you want to drive inference for a longer period of time, energy consumption becomes important, and if it does, it's very critical that you operate on the right-hand side of the graph. The right-hand side of the graph gives you the highest advantage in terms of performance and in terms of efficiency. If you're looking for ease of use, if you have a model that is being developed on FP16 or an FP8 or an FP4, you don't want to do any kind of transformation from float to fixed point, you obviously could operate on the left-hand side. When you do it on the left-hand side, obviously it does come with the baggage of power, but that's okay. Depending on the use case, you can kind of switch. So you give the choice to the developers, and depending upon the need, you can choose one flavor or the other. Now, when you start looking at enabling inference on the edge, what are some of the infrastructure investments we have done? I'll touch on a few of them. First thing is, if you happen to have, let's say, a PyTorch-based model, which is quite popular these days, you can absolutely use Executive Torch. We have a very strong relationship with the PyTorch infrastructure team. You could quantize these models, use the Executive Torch, and run it on the Hexagon NPU engine, no problem. We also have the Qualcomm AI Hub. Qualcomm AI Hub is a product coming from Qualcomm, wherein if you happen to have native graphs, we support the quantization, we support the compilation of these models, and you can create a binary that you can execute on device. You also have Nexa ML. Nexa ML is a third-party vendor that we work with. They also support converting these models, quantizing these models, and creating a binary that is friendly for Qualcomm silicon. So again, multiple paths reaching the same endpoint, same goal post, working with either community or with third party or using Qualcomm product line to really drive inference on the edge. I'll expand a little bit on the Nexa AI. Nexa AI is a specific company. It's a startup company that we have partnered, I would say give or take, for the last 12 months or so. They work specifically on large models, specifically on LLMs, on LVMs, on LMMs. They have an SDK called Nexa SDK, and they're able to support any model coming from any framework, and their SDK is able to, again, quantize it as part of their flow and create a binary that is either suitable to run on CPU or GPU, which is a general purpose compute machine, or the Hexagon NPU. If you're very familiar with OpenCL, you could do the GPU with OpenCL. If you want to use Vulkan, you can use Vulkan on the GPU. If you want to use the GGML format, that also is supplemented and supported using Nexa on the CPU. But if you want to create a custom binary using custom operators, the Nexa SDK also supplements and support that to run on Hexagon NPU. Again, plenty of choices. Really encourage the developers out there to kind of check it out and obviously give us feedback on how else we can improve on things to make inference on the edge a lot more easier. On the AI Hub, similar statement. As I mentioned before, This is a product that we launched, give or take, about 12 to 18 months ago. We started a journey with Android, then we expanded this into Windows and Linux as well. You can pick up any model of your choice, and the Qualcomm AI Hub provides you the infrastructure to convert these models so that you can easily execute this on a Qualcomm backend processor. One good thing about the Qualcomm AI Hub is it also hosts a lot of devices. So which means if you're interested to understand what would be the anticipated performance could be in terms of tokens, in terms of the memory that it takes to deploy this model, the power consumption, all of those numbers is provided by the AI Hub using those reference devices that's hosted on Qualcomm AI Hub. And last but not the least is the Executive Torch Delegate. This is something that we launched in the PyTorch conference a couple of weeks ago. This was a couple of years of work with the PyTorch team, and now we have this live, we have this running, and it supports both the CPU, the GPU, and the NPU. So again, multiple avenues to get to the same endpoint from an inference standpoint. And if people are more familiar with PyTorch and they want to use Executive Torch, we highly encourage them to get it done. From a performance standpoint, it doesn't really matter. You take the Nexa path or the AI Hub path or the PyTorch path, you get pretty much the same thing. Okay, and these are some of the initial support for the models that we have as part of Executive Torch 1.0. And these lists that we have on the left-hand side is continue to expand. This is something that we released at the PyTorch conference, and now we are actively working with the PyTorch community to kind of expand the portfolio of the models that can be run on the edge. So with that said, I'll hand it over to George from Layla Networks. He'll walk you through a real-life example and how he has used the infrastructure provided by Qualcomm to really make things a lot more exciting. Okay, here you go.
Thank you very much. Thank you. My name is George. I'm the founder of Layla Network. So Layla is an app which runs local LLMs on your phone. So you can think of it as a combination of ChatGPT, Google Gemini, and Character AI, all combined. But the thing is, it runs locally using only your phone's hardware. So it doesn't require any external services. It doesn't require internet connection. So today I would like to share with you guys just my journey in building Layla and my experiences in building AI features under the constraint of mobile hardware. And also, just to show you what's possible with LLMs on mobile today. And also my vision of Layla and both AI in general for the future. So I started building Layla back when ChatGPT just released, a little afterwards. And when ChatGPT was released, everyone could see the potential, right? You see it in TVs, movies, sci-fis. You could see that AI is going to be integrated with our lives. But there was one problem, and it's online. So if something is going to be so deeply integrated with your life, if it's online, you're not going to have privacy. Your conversations, your data could be leaked, and it already has. So ChatGPT has leaked the conversations of millions of users just recently. And you're not going to have reliability. For example, your internet could be down. You could be in a remote area with no access to your personal companion. So this is why I started building Layla. I wanted to see if local LLMs can run on mobile. So when I first started, it was Lambda CPP was still just one file, and 3 billion parameters were barely coherent. But it actually worked, and the first reviews came in saying, okay, I didn't know this was possible, it actually works. And I knew that I was very early, and the hardware is going to improve, LLMs are going to improve. And almost 2 years later, Layla has become much more than just an app that runs LLMs. So Layla has a lot of features, and these are all built upon running LLMs. And you can see there's things like background inference, long-term memory, image recognition, text-to-speech. So all of these apps in Layla, you can add or remove them as you see fit. So this is what makes it personalized. So if you don't want a feature, just remove it so it doesn't take space. And Local LLM has many use cases, and Layla supports them. You can have assistant, friend, role-playing, image generation. So all of these comes with specialized small language models. So we should start calling them specialized language models instead of small language models. And these are fine-tuned by the community. So each of them, they're good at, for example, assistance, or you can good at emotional connection, so talking as if a friend, or role-playing, creative writing, what have you. So going back to the LLM, this is the backbone of all the features. So for the technical people, Layla allows you to load your own LLMs. So you can choose whichever formats that's supported. It could either be GGUF models or could be PTE models. And you can also connect it to OpenAI endpoints. So if you have, let's say, an inference engine running on your PC, you could use Layla to connect with it. So you have the best of both worlds. And my philosophy in building Layla is to make it open. So you're always able to choose what LLMs you want, and you're never locked into a specific vendor. And for the technical people, you can configure advanced settings like temperature, sampler settings, and KV cache quantization, and different hardware accelerations, which I will get into later. So in order for Layla to be more than just a technical demo, we want you to use it every day, right? So the first thing we do is integrating it with your operating system. So here you can see Layla can actually replace Google Gemini as your phone's assistant. So you hold the power button, you run, it works the same as Gemini, except that it runs a local model instead of a cloud model. And you can see here, it's actually running a text-to-speech model here. So it's a two-pass speech to text. And you can see it's actually triggering an agent, which drafts an email for you. And it calls the agent, calls the tool in the agent, which will open up your email app. So this is one example of how local LLMs can perform the same tasks as cloud, but on your phone. So this brings me to Layla's agentic framework. So Layla is built to be personal, customizable, and this framework is no exception. So the core of the framework are the different tools the agents can use. And these tools vary from HTTP requests, opening email, sending SMS, sending alarms, creating calendar events. So these tools, you can actually configure them. You can create your own agents and choose which tools to use. And you can mix and match them, because everyone has different workflows, right? Everyone prefers different ways to do things. So you're actually able to create all of this inside the app and create an agent that's personal to you. And this is one example of an agent that our users have created. So you can see that the agent triggers by Q&A intent and a cooking query intent, or a cooking query intent. So this is actually an example of we're combining classic ML, such as sentiment detection and intent detection, with agents and with LLMs. So because on phones, you have very limited hardware, and each token and each context length that a token uses is very valuable. So this is different from the cloud, where you can just send the whole tool into the cloud model, and it'll decide what to call. But on mobile, we can't do that. So we fall back to traditional ML techniques, which works just as well. And once the tool is triggered, you can see the LLM tool call switch is on, which means it actually passes the tool to your local LLM. And you can see the query here is written in natural language. So when you pass the tools to the LLM will understand the tool signature and call the right tools. And in this example, you can actually see it calls the web search tool twice. And the instructions given to the LLM is do one query first, and then with that results, expand the query and search the web again. So this is an example of a deep research agent that you can build yourself, and it runs completely locally. And another very interesting agent that our users have built is the role-play agent. So this is an example where an agent can interact with a different model, not just an LLM. So this one takes the conversation that you have, and it generates a stable diffusion prompt. And then it passes off the generation to a stable diffusion model, which is running on Qualcomm's NPU, by the way. So this image generation takes less than a second. So it does not disrupt your conversation flow at all. So you can see the agents is very flexible. You don't need to call LLMs. You can call other different models, such as stable diffusion. And another application that I would like to share with you is our implementation of long-term memory. So having an LLM remember your conversations is a very difficult topic, even on cloud, but it's even more so on mobile because it's really compute intensive. So we had to split this process into 4 parts. The first 2 is just taking the raw memories, which is your conversations, the text for the conversation, and we generate embeddings out of this. So this process is fairly fast, so we can do that in real time. But then generating summaries out of those raw memories and then creating the knowledge graphs out of it requires a specially trained LLM which generates the knowledge graph. And this is too compute intensive to do in real time. So what we actually do is we offload this, so when your phone is plugged in and you're not using it, it actually does this in the background. So usually that's when you're sleeping, right? And in fact, coincidentally, this is how memories work in humans. When you sleep, your brain combines your memories, summarizes them, and so this is an example of how on mobile, our hardware constraint actually makes it really similar to how our human brain works. And recalling just does this step backwards. So you take the knowledge graph information, and take the summaries, and then you inject the summaries into your conversation context. So putting all of this together is our characters, obviously. So you want to have this as an AI companion with your memories, with your agents. And you can see this character is actually using sentiment detection to change their expressions based on your conversation. And you can do voice chat with it, which uses text-to-speech and speech-to-text models. So combining all of this makes the companion come to life on your phone. And unlike Grok is doing similar things to this, but again, this is all on your phone, no internet needed. So going back to running LLMs, because that's obviously the backbone of Layla, and your phone can run LLMs. And this benchmark website is actually, these data is submitted by our users, and they are running on real consumer phones. And this will give you an idea of what LLMs and what performance you can expect from your phone. So the benchmark data is, so for example, the phone could be old, the phone could heat up. So it's a really good representation of real world conditions of running LLMs on your phone. So to get the most out of running an LLM on your phone, you have to choose one. And these are the 4 factors that's the most important in choosing. From the hardware side, CPU and RAM. So CPU governs how fast of an LLM that you can run, and RAM determines how big that you can run. So obviously, the bigger LLM are more intelligent. And the more parameters an LLM has, the more intelligent it is. And quantization changes the LLM structure to run it better on different hardwares. For example, the Qualcomm NPU works best with 4-bit interleaved quantization. So, based on the benchmark site and what your phone has, you can experiment with loading different LLMs and get one that you feel is good. And for the hardware acceleration, Layla runs on the CPU, GPU, and NPU. And a lot of users actually come to me asking, after using Layla, they think, what phone should I use to run LLMs? And I always tell them, get the Snapdragon phones. And I'm not saying this because Qualcomm invited me. So the NPU is really important here because in a real-world scenario, you're going to have background apps. Your phone is not just running LLMs. So the RAM savings and also the power efficiency is really important. So that's why using the NPU is really important in running LLMs. And so these are my recommendations for different use cases. So the local LLM community fine-tunes a lot of models. Different ones can be used for different things. I use Gemma 3N, which is the official one from Google. It's for everyday tasks. And the fine-tuned ones are good for role play. And Impish, good for smaller sizes, excellent for role play. And if you have a really good phone, you can try 12 billion models. So there's a lot more models that you can find on Hugging Face. And these are in general, 3 to 4B is good for everyday tasks. 8 billion model is good for conversations. where you wanted to remember details, scenarios, and 12 billion is good at everything, but you need a really good phone. And the Q4 quantization sizes provides the best balance between speed and loss of intelligence. So to conclude, I think local LLM is the future because, first of all, I've said all the parts about the users where you have privacy, reliability, but even in the business side, you see the big cloud providers, the model providers, they're losing billions every day, right, just to run the models, and it's not sustainable. So everyone will be moving towards local in the future. And I think this is the same situation we see where computers move from these huge mainframe into the homes, your PC, and then moving onto a smartphone. So AI will do the same. Tomorrow we can have AI that's running in the palm of your hand. Right, thank you.